Hello everyone, welcome to the lecture 15 in the course Diffusion in Solids. So like the last 2 weeks, this week will be or this lecture will be the tutorial lecture where we will try to solve some problems or questions on the concepts that we have learned over this week. So we will see some problems on the crystal structure, the vacancy concentration and on the random walk. So here are a few keywords, and as I always say that I will display the question, you please pause the video, try to solve the questions for yourself and then see whether your answers match or not. So the question number 1, this is fairly simple. The Bravais lattice which is not present for cubic crystal system is. So you remember that there are 7 crystal systems, and actually if you see that there are 4 different types of Bravais lattices, that means a primitive, a cubic, a body centered, face centered and also a base centered. So actually it should be 7 into 4, 28 Bravais lattices, but they are not, and they are only 14 exist because of certain equivalency that is established. So now the question here is that which is not present for the cubic crystal system. So the face centered cubic, we know it is there, body centered it is there, primitive is there, base centered is not there. So you may want to think, although as I said that this is not really a part of this course, but still I thought I will just show you why the base centered cubic crystal structure does not exist is because the base centered cubic can be also visualized like this. So you can see here these are the base centered atoms. So if there was base centered cubic, it would have been corner atoms plus these base centered atoms. But this base centered cubic structure can be also visualized in a way such that you reproduce a tetragonal Bravais lattices. So if you see 2 base centered cubic unit cells together, you can also generate a tetragonal Bravais lattice. So you remember that the Bravais lattices, these are the conventions which one to take, and now usually what is preferred is a Bravais lattice with a lesser number of atoms per unit cell. So if you count the number of atoms per unit cell in a base centered cubic, you will have 8 into 8 1. So 8 into 8 1 plus 1 by 2 into 2, that is 1 more. So that will be 2 atoms per unit cell. Whereas you generate a simple tetragonal Bravais lattice, it will be 8 into 8 1 atom per unit cell. So usually the lower number of atoms per unit cells are preferred. So therefore here the correct answer is B. So the base centered cubic does not exist. Coming to the question number 2, for a BCC lattice, the planar density is maximum for 100 plane, 111 plane, 110 plane, or all have same planar density. This we have also derived. If you remember that we said that planar density 100 is equal to 1 by a square. I suggest that you go back to the previous lecture and try to calculate it for yourself. How do you calculate the planar density? Basically, it is the effective number of atoms on that plane multiplied by the area divided by the area of multiplied by the area of the atoms, 1 atom, and divided by the area of the plane. So if you calculate for 100, it is equal to 1 by a square. For 110, it is root 2 by a square. For 111, it is 0.577 by a square. So you will see that the 110 has the maximum planar density. So therefore the correct option is the C here. Moving on to the next question, this is a simple recall question. In an ionic crystal, the formation of a Schottky defect involves. So displacement of an atom into an interstitial site. No, this is not correct. So the Schottky defect is, if you recollect from the previous lecture, it involves a simultaneous removal of a cation and anion. So, remember that it is an ionic crystal, so charge neutrality has to be maintained. So, therefore, it is a simultaneous removal of cation and anion. So, the correct option is B here. Moving ahead, which of the following will be a Burgess vector for pure nickel? So, here A is the lattice parameter in these options. So, pure nickel, if you know, pure nickel has a FCC crystal structure, and we have seen the Burgess vector for FCC is actually A by 2 110. So, the correct option is D here. Moving ahead to the next question. So, the root mean square displacement of B atoms in A matrix after n jumps is L. Okay. So, let us say there is a diffusion of B or movement of B going on in A matrix. So, after n jumps is L. Hypothetically, what changes can increase the root mean square displacement to 9L? Okay. So, hypothetically, what changes can increase the root mean square displacement to 9L? Let us see first that the root mean square displacement is equal to root n times lambda. So, where where n is equal to the number of jumps and lambda is equal to the jump distance. Now, L is given that after n jumps the root mean square displacement is L. So, that is equal to, let us say, root n1 into lambda 1, and 9L, that means after certain changes it becomes 9L, it is equal to root n2 times lambda 2. So, if you take the ratio of these, then 9 is equal to root n2 by n1 into lambda 2 by lambda 1. Now, let us evaluate each option and see which gives us the product equal to 9, which satisfies this equation. So, option A is increase of lattice parameter by 3 times while number of jumps remain constant, which means that lattice parameter by 3 times, that is lambda 2 by lambda 1 is equal to 3 and n2 by n1 is equal to 1. So, number of jumps remain constant. So, the product of this 3 into 1 is 3, which is not equal to 9, therefore, option A is not correct. Option B is, so remember you will have in assignment as well as later in your exam questions with multiple correct answers. So, therefore, please, although there it will be indicated, here I have purposefully mixed it up so that you analyze every option carefully. So, now here in the second option you have increase on number of jumps by 81 times. That means root n2 by n1, so n2 by n1 is 81 or root n2 by n1 is equal to 9, while the lattice parameter remains constant. So, lambda 2 by lambda 1 is equal to 1. Please remember, here we are talking lattice parameter, you may say lambda is jump distance, but remember we derived this for lattice, where typically the jump distance is of order of the lattice parameters, means we derived it for crystals. So, there the jump distance is of the order of the lattice parameter. So, in this case option B, you see that lambda 2 by lambda is 1, lambda 1 is 1 and root n2 by n1 is 9 and 9 into 1 is equal to 9. So, this is correct. So, option B is correct. Then say a C option is increase in number of jumps by 9 times and the lattice parameter by 3 times. So, that means lambda 2 by lambda 1 is equal to 3, n2 by n1 is 9 or root n2 by n1 is equal to 3. So, therefore, 3 into 3 is equal to 9. So, this is also possible. So, this is also a correct option. Option D is increase of number of jumps by 3 times. That means n2 by n1 is 3 or root n2 by n1 is equal to root 3. Whereas lattice parameter increases by 3 times. So, lambda 2 by lambda 1 is equal to 3. So, the overall product is 3 root 3, which is not 9, and therefore, option D is not correct. So I hope you understood how to solve this or how to approach this problem. The correct options are B and C. Moving ahead, this is again a recall question. Although in the stacking fault is the term we only listed in our categories of defect, but just to tell you, stacking fault is a planar defect that occurs due to an irregularity in the stacking sequence of atoms. So here, for example, the one of the stacking sequence possible typically in FCC is ABC, ABC. So you can see this is CBA, CBA, and so on. When there is a stacking fault, which is displayed here in the pink colored atoms, you can see that instead of A, there is again a C layer being repeated. So here this is a stacking fault. So you see here that this is not CBA now, it's a CBA, CBC, and so on. So this region which occurs due to the stacking sequence irregularity is known as stacking fault. And if you have multiple stacking faults also possible, so then sometimes you look at what is the distance between these two stacking faults, and it has a certain influence on the mechanical behavior of the material. Then part B of this question is fairly straightforward. Dislocations enable plastic deformation in the crystalline solids by allowing planes of atoms to slip past each other. Remember, plastic deformation. So moving ahead to the next question, what is the largest sphere that can fit in the octahedral voids of FCC unit cell? So this, please, I strongly suggest that you try first yourself, then only look at the solution. This was also explained in the lecture. So this is how, so in an FCC, first of all, where is the octahedral void? So one of the octahedral voids is at the body center, and then rest of the voids are at the edge center. Okay, so you can see here, actually if you count, then you can also tell that how many octahedral voids are there in the FCC. Okay, so you can see here that actually edge is shared by 4 unit cells. So there are 12 edges. So 12 into 1 by 4 is 3 plus 1 at the body center. So there are total 4 octahedral voids in the FCC. And now if you want to calculate, so what you do is that here this is the interstitial atom, here is the, so this is the parent atom or the regular atom, here is where the interstitial atom would be sitting, and again here is the regular atom. So therefore the R plus 2R plus R is equal to A. This is the distance between these two is A, which is the lattice parameter. And we know that for FCC root 2A is equal to 4R. This comes by this. Remember, these atoms are touching each other, and therefore A is equal to 2 root 2R. So if you put it here, then you get twice R plus R is equal to 2 root 2R, or small r is equal to root 2 minus 1 into capital R, which is 0.414 R. So that is the largest sphere that can fit in the octahedral void of FCC unit cell. I do suggest you to please try out this for the other unit cells and other type of voids as well. Then coming on to the question number 8, calculate the equilibrium number of vacancies per cubic meter for copper at 1000 degrees centigrade. The free energy for vacancy formation is 0.9 eV per atom, and the atomic weight and density at 1000 degrees are 63.5 gram per mole and 8.4 gram per centimeter cube respectively. Now here, see, remember, when we derive the relation, what we have derived is equilibrium vacancy fraction, which is XV equilibrium is equal to exponential minus delta G Vf by kT. Again, please remember, depending on what units you are putting for G, you have either R or K here. since it's EV per atom, we stick to K here. Now, this is the fraction. Now, what do you mean by the fraction of vacancies? Fraction of vacancies means that how many number of vacancies are there divided by the total atomic sites in the crystal. Okay. So, therefore, or in the material. So, therefore, XV equilibrium can be written as NV, which is the number of equilibrium number of vacancies divided by N, which is the number of atomic sites. So, NV by N is equal to exponential minus delta G by KT. Now, how do I estimate N? So, N I can estimate by a formula which is Avogadro's number into rho by the molecular weight. So, remember why I can use this formula is you may see that rho is nothing but density and W is atomic weight. So, that is the N0 divided by the volume. Okay. So, this will give me the number of atoms per in the volume that is given per cubic meter. I have to calculate. I have to calculate the number of vacancies per cubic meter. That's why I am estimating the number of atomic sites per unit volume. So, which is N0 into rho by W. So, rho is density, N0 is Avogadro's number, W is atomic weight. Now, here Avogadro number we know 6.023 into 10 to the power 23. Pay attention to this. This is 8.4 multiplied by 10 power 6, because remember here it is centimeter cube, whereas we will be using the standards or not in the standard, sorry, we have been asked to calculate per cubic meter. So, to convert it into per meter cube, I put 10 power 6. Remember, it is per centimeter cube. So, it becomes 10 power 6 here, divided by 63.5. This is gram per mole. Okay, since both numerator and denominator it is gram. So, gram I don't need to convert, but centimeter cube has to be converted to meter cube. So, this gives you 8 into 10 to the power 28 atoms per meter cube. Now, you can put in this formula NV is equal to N into, so 8 into 10 power 28 sorry, into exponential 0.9 divided by K. Again, remember K because we are putting G in EV or delta G in EV. So, K also has to be put in EV, which is 8.6 into 10 power minus 5. And temperature always in this formulas is always in Kelvin. So, 1273. I am just highlighting this because in the assignments or in the exam, people tend to make this mistake of the unit conversion, and then you end up in a wrong answer. So, if you put everything correctly, you get 2.2 into 10 to the power 25 vacancies per meter cube. Question number 9, a pure metal has a melting temperature of 1200 Kelvin and the free energy to form a vacancy is 1.2 EV. Calculate the equilibrium fraction of vacancies at 300 K and 1200 K, and use the Boltzmann constant in EV as this. So, you may see that this is a fairly straightforward question. The delta G is given. So, you calculate directly XV. And if you put the correct values, what you get is XV is equal to 8.91 into 10 power minus 6 at 1200 Kelvin, and XV at 300 Kelvin is 6.3 into 10 power minus 21. So, one thing that you notice from this question is that when you come from 1200 Kelvin to 300 Kelvin, see the huge change in the number of vacancies that come. So, you have from minus 6 to minus 21. So, that means there is a lot more reduction in the vacancy concentration, or if you look at from a reverse perspective, that means when you increase the temperature, the vacancy concentration enhances significantly, and that is why you will see later that the diffusion coefficient exponentially varies with the temperature. So therefore, because vacancies act as an important mechanism for diffusion to occur, and therefore increase in their concentration also leads to the enhancement in diffusivity. So you can clearly see the numbers impact of temperature on the vacancy concentration. Question number 10. If the diffusion coefficient D is equal to 2 into 10 power minus 9 meters square per second and the diffusion occurs in 3 dimensions, what is the mean square displacement after 1 second? Assume a cubic geometry. So we know that the D is equal to R square by 6 tau. So here R square is given 2 into 10 power minus 6 into 6 into 1 here, and therefore R square is equal to 1.2 microns. The second part is a diffusing particle undergoes a random walk where each step has a length of 0.1 nanometer. The particle takes 106 steps. What is the root mean square displacement? So remember, sometimes in the questions I have put this again. You may think that these are very simple formulas, but the intention here is also to make sure that you use the correct formula. You also see the slight difference. Here we are asked mean square displacement, here you are asked root mean square displacement. So be careful what you are calculating. So for a true random walk, the root mean square displacement is root n times lambda. The numbers, if you put correctly, you get 1.02 nanometers. So the last question is related to the Scilab demonstrations that we understood. So again, for this also I strongly advise you try to generate your Scilab plot and see whether you get the same output as shown in the next couple of minutes. So a thin layer of element B is sandwiched between two blocks of element A. The assembly is heated isothermally at a temperature T for a time T. The total amount of element B can be taken as MB and use Scilab to plot the concentration profile as a function of time and show the effect of diffusion coefficients on these profiles. So you are, I'm sure, very well aware of this problem which we dealt with in our second week in the solutions of diffusion equations. So this is a sandwich geometry where you see that this is the scenario where you had the B atom sandwiched between A, and after time T the B starts diffusing into A, and the solution for this is given by a Gaussian function, which is C of x comma t is equal to m by 2 root pi dt exponential minus x square by 4 dt. Now what we need to do is to write a Scilab code. So we have seen that you can use the editor in Scilab to write these codes. You can take the inputs, you can take the skeleton of the code from the previous examples given in the lectures and use it. The formula is what needs to be changed primarily. So you can see here what I need from the user are the input parameters, that is M, D and T. Remember, in the question it is said that show the effect of diffusion coefficient. So I am asking user to define D, T and M. Now and again it is dependent on you. You can also choose a fixed value of M. It is up to you. You can only show the variation of D and T. That is also fine. So you say M is equal to input, enter the mass M. So this prompt will go to the user when the code is executed. Again, D is equal to input, enter the diffusion coefficient D. You can also, once you are more familiar with doing the code, you can also input temperature from the user, give your own D naught and Q, as I also showed you in one of the examples, and then let the user enter T and you study the influence of T actually. So that is also possible. All kind of combinations you can try. Then if you are asking the user to input the time values in days, then you convert this T into seconds. So usually you will not ask the user to input the values of time in seconds. It is difficult. As a user, you may it may be more convenient either hours or days. Accordingly, you can put a formula in your code. Then you define the range of x values. So, what may be the possible range of x? This can depend upon the dimension of the samples you perceive. Then these are the setting of the plot. So, these are different colors for different curves depending on how much values of time you are ready to give. Then, as I said, that because we are giving multiple values of time, so we have to use what is known as the for loop. So, you can see here for I is equal to 1 to the length of t, that means how many t values we have given. For each t, this formula will be executed, m by 2 root pi dt, and this is power 5 basically, and then using this you will calculate c is equal to this whole thing multiplied by exponential of minus x square divided by 4 dt. Again, ti means for every time it will be calculated. And then you give the plotting commands, which is the plot, x label, y label, and title. And then again here the legend for the overall graph. And then finally you click show. Again, as I said, that the main intention for you is to not to memorize the code, but to understand the code and use it to see how the different parameters can impact the diffusion profile generated. So, for example, you see that when we execute, we get this command, enter the mass m, enter the diffusion coefficient d, and enter the time values. So, let us say if I enter d as 10 power minus 11, and then I entered 3 different times, 1, 5, and 10 days. So, the graph that I will get is something like this. So, you can see that this is for 1 day. So, the time I entered is actually 1 and 10. So, you can see the red color is the 1 day profile. After 10 days, it starts spreading. So, you can see a dip in the initial concentration at the center. That is why you remember it is called as instantaneous source. So, there is a spread in the profile. Now, if the diffusion coefficient I increase by 1 order of magnitude, 10 power minus 10, then you see the effect. So, here the profile now becomes broadened both at t equal to 1 and t equal to 10. Diffusion spreads, the B atom spreads more. So, very clearly it shows you that how the time and the diffusion coefficient impacts the profile. So, like that you can try several parameters. You can let me know if you write something interesting code, we will be happy to see. So, with that we will close this tutorial lectures. Please let us know if you have any further doubts. Thank you.